Hello folks, after a long time I'm again online. So it has been a pretty busy week or 2 weeks on exams, on setting up question papers, examining answer scripts and so on. So I'm slightly free, and immediately I'm jumping into what I do, always making videos. So today I have got 2019 February March paper 4.2, and the question number is 6. It is concerned with the chapter alternating current of current. So it says that the first question is 6a. Define the capacitance of a parallel plate capacitor. So defining only capacitance and defining the capacitance of parallel plate capacitor are different, because in parallel plate capacitor we have to express the charge in terms of charge stored in one plate, because in both plates, if we take the total charge, it will be 0. So we have to state charge deposited in one plate compared to the PD across the plates. So number B, a student has 3 capacitors. 2 of the capacitors have a capacitance of 4.0 microfarad. So that means C1 is equal to 4 microfarad, and again C2 is equal to 4 microfarad. And one has a capacitance of 8 microfarad, so it is C3 is equal to 8.0 or 8 microfarad. Draw label circuit diagrams, one in each case, to show how the 3 capacitors may be connected to give a total capacitance of 1.6 microfarad. So we have to obtain 1.6 microfarad first out of these 3. So what we have to realize is 1.6 is lesser than all of these things individually. So what you can just suppose is maybe a series combination gives that. Maybe a series combination of these things give that. So this is the first trial. So let's try. So if I do 1 by 8 plus 1 by 4 plus 1 by 4, it will be equal to, so this is 8, 1 plus 2 plus 2, and that's equal to 5 by 8. This is 1 by C. So C should be equal to 8 by 5 equal to, yes, 1.6. So my guess worked. So what I have is I'll obtain 1.6 if I connect all of them in series. So this is the formula for series. So series means that, so this will be 8, this will be 4, and this will be another 4. So this is 8 microfarad, this is 4 microfarad, and this is 4 microfarad. So these things will give us 1.6 microfarad. Now the next one is 10. So 10 is definitely bigger than this as well as this. So that means there should be some sort of parallel arrangement. But if I do 8 plus 4 plus 4, it will be 16. So it must be 8 plus something lesser than. So let's do it like this. If I connect 4 and 4 in series, it will be 2. So if I connect this 2 to 8, this 2 added to 8, that should occur in parallel. It should be 10. So 4 and 4 should be in series to obtain 2, and that 2 should be connected to this 8 in parallel, which gives us 10. So what I do is, so I must have this 4 and 4. So this is a 4 microfarad, this is 4 microfarad, it's in series, gives 2. This connected with this 10 microfarad. So this thing should give us that 12. So 2 plus 10 equal to 12. So sorry, 2 plus 8, sorry. So 2 plus 8, this is equal to 10 microfarad. So I often make mistakes while speaking, so I corrected it timely. Then the next question is a capacitor C of capacitance 47 microfarad is connected across the output terminals of a bridge rectifier not shown here properly. So this block diagram means bridge rectifier. We have the capacitor here, this R. So this is used for smoothing. This is the AC source. The variation with time t of the potential difference V across the resistor R is shown in figure 6.2. So this is the variation. So we have put a charging curve here, discharging here, charging here, discharging here, and so on. Use data from figure 6.2 to determine the energy transfer from the capacitor C to the resistor R during time t1 and t2. So from t1 and t2 time, we have to calculate the energy transfer from the capacitor to the resistor. So one thing that we have to remember is that the capacitor transfers energy to resistor only during the discharging phase. So that means in this phase, and in this phase, and in this phase. What we are given in the question is from T1 to T2. So that means we have to calculate the energy transfer only from here to here. This is the phase in which energy is given from the source to the capacitor, source or rectifier to the capacitor. So here we have to do from capacitor to resistor. So we have to go only for this phase, only for this phase. Though it says T1 to T2, we have to go from here to here. So this is charging phase, this is charging phase, and this is discharging phase. So our energy will be equal to, so delta energy is equal to 1 by 2 C initial V1 square. So V1 square is here, the V is equal to 6, 8 middle. So it is a 7 square minus 1 by 2 C. Then here the voltage is, PD is 4, so it is 4 square. So it should be 1 by 2 into 47 into 10 to the power minus 6 given here. In bracket 7 square minus 4 square. So when I do the calculations, it will be equal to 0.5 for 1 by 2 into 47 exponent minus 6 into bracket 7 square minus 16 bracket close equal to, so it comes to be equal to 7.755 into 10 to the power minus 4 joules. So if I write it in 3SF, which I often do, and which is correct also, so it will be equal to 7.76 into 10 to the power minus 4 joules. So it is 7.76 into 10 to the power minus 4 joules. So the complete answer for this question.